Thank you very much for that introduction, and thank you everyone for being here. So, first of all, this is John Ward with David Fernandez Duque and Juan Aguilera. I will briefly introduce reverse mathematics and have time a little bit of motivation to the work we have been doing. So, if you know anything about reverse mathematics, you can set, as I like to talk about it, as a research program within foundations of mathematics. Like, if I want to investigate something about a theorem that I like, I would take reverse mathematics as my research program to say something about its foundations. And that's how Stephen Simpson also motivated in his very famous book. So briefly, we are settled in second-order arithmetic, and we have some subsistence of it that will allow us to play with ordinary mathematics. So we have, as always, RCA 0, our base system, which is the system that includes Robinson arithmetic, induction for sigma 01 formulas, and delta 01 comprehension axiom scheme that states the existence of computable sets of natural numbers. This, I know, most of you know. Then, in the hierarchy of these systems, we have a stronger one with Koenig's lemma, WKL, that adds a weak form of Koenig's lemma, stating that every infinite binary tree has an infinite path. That is the existence action of weak Koenig's lemma. And finally, we have a lot of infinite subsistence, of course, but the last one I will talk about is ESI 0, which has the axiom scheme that allows the construction of sets defined by arithmetical formulas. So you have been in the previous weeks. You already know a lot of things that we can do in these systems and in others. Now, I will do today and tomorrow a little bit of a whole proof within one of these systems and a reversal of a theorem that you can say I pick randomly from ordinary mathematics. So this theorem is called the Mountain Pass Theorem, which is a theorem that has to do with critical points in non-linear analysis. It's a very cool theorem. We will explore it just in the meta language in the real world first. And for that, we need some definitions. First of it, we will work in Hilbert spaces, so we have access to an inner product. And as usual, take H Hilbert space and a continuous functional. It is a function from H to the reals. We will write as usual that I is C1 if it has a derivative at every point, and this derivative, which will be a function from H to H, is also continuous. If in addition this derivative, this function is locally Lipschitz, I will write C11. This will be an important hypothesis later. And, well, we can comment about what it means, the derivative, but to just think as usual. There are nuances, but if I have time later, I will address them. The other very important definition that we will be needing is this one. So let's take of course, yes. No. So, like, the idea is really that you have your functional I H2R. Let's say this is first Banach, not just normal space complete, not Hilbert. So we really can define the notion of derivative in a Banach space, but it really is a function that goes from H to the space of bounded continuous operators. In this is Frechet. So we can talk about the space of Banach of bounded operators in full generality in set 2, because even if this is complete, we cannot assess that the space of bounded operators is even separable. So one trick is that in Hilbert spaces, we have access to how it's called, the Rees representation theorem that will allow us to make a leap and just have exactly what is here. So there are no answers there, but in this talk I will just say that I have something that behaves as a derivative. So it has everything that I want, like a chain rule, like it has a product rule, like it just gives me what I need. You can imagine this as I think the best thing that you can imagine is like to be in finite dimension. So this I prima represents the gradient. So if you recall some of that, you can grasp it. But if not, just think about R, and this is my derivative, like the usual Newtonian thing. It's not at all trivial, but I can just put the definition in the system, and it will work. Like I can define it as a limit, exactly as a Frechet derivative. But yeah, think about it from R to R. Cool. Maybe we can do the math later to show how it can be done in at least in the meta language, because formalized in C2 can have we can have problems. So we can just put as a definition. We have to put it as a definition if we don't have to. We don't want to increase really the strength, because, for example, Rees representation theorem is an ACSE theorem, so it has nuances. So just take it as a given thing. Okay. Now the definition, the following definition is the Palais-Mail sequence. So in a Hilbert space and a C1 functional, we say that the sequence of elements of H is Palais-Mail if the sequence of images is a bounded sequence. This would be in R, of course, and I prima of Xn converges to 0. And we say that I satisfies the Palais-Mail condition, it is PS, if every Palais-Mail sequence of elements of H has a convergent subsequence. So this is a very unconstructive condition, right? I have that kind of sequences, and I always can have a convergent subsequence. It's kind of a compactness idea within these kind of sequences, sequential compactness idea. So these are the only technical previous definitions I need to state now the theorem. So this is a theorem from 1973 by Italian mathematician Antonio Ambrosetti and American mathematician Paul Rabinowitz that says, let H be a Hilbert space and let I be a C11 functional. That satisfies the Paris-Mail condition. Suppose that I of 0 is 0 and the following two geometrical hypotheses are satisfied. We have there exists rho and alpha positive such that these two things happen. Whenever the norm of U is rho, then its image will be greater or equal than alpha, and we have the existence of another point such that it has bigger norm than rho and such that its image goes below 0. Then it has a critical value. So it's a critical value means the value that the critical points have. So a critical point, as always, is where the derivative is 0. And the critical value is the image of that critical point. I'm saying this. Critical point and critical value. So I am saying that this has a critical value, that this has a critical point, which is a theory by itself in analysis, like to have conditions where I can have where I can find critical points, and then I also have the image of that critical point, and moreover I can characterize it as this. So look at gamma. Gamma is the set of all the paths that go from 0, 1 into H that have fixed end, beginning and end in 0 and end in 1 for the given B and 0. I can characterize the critical value as taking first the maximum of all the paths that will be in the surface of my functional, taking all the max, and then looking at the minimum, in fact the infimum of those. I think if I do I will let's see how what we mean in a very in one dimension. So I'm saying like I have I just said or it was so critical point and critical point the critical value is the image of a critical point. So imagine this. So I'm saying I have 2 points. Let's call in R from R, like in the with the functional R to R. So I have rho minus rho. I am saying I have some rho that if, of course, the functional has to define totally, and I am saying let's call this vector. This vector will have U1. It has norm equal to rho. So if I had to say this is alpha, I'm saying this the image of has to be bigger or equal, and I also have to do the same for them. Or the other one in this context, only two of those has U2. Only these two have a norm equal to rho. And I also have, this is very important, U of 0 has to be 0. So more or less I have to do this, and the other thing is that I will have some B that has to have an image below the 0. Something like that. And this can do this and whatever. So what it's saying here is like very, do you know this theorem, you know? If I have this kind of points, in between of them, I will find maybe this one, maybe it nothing, not it needs not to be this, of course, the U. But if I have to connect two separate things with a continuous function, it will have a critical point. In this case, the maximum needs to be a minimum. That's a version of Rolle's theorem. If you recall that from when you were and it's indeed the one-dimensional case. But where are the mountains here? The mountains are just a step forward, right? So the theorem is very basic. So imagine we have two valleys. Two valleys like these ones in this graphic have this geometry that I rho and b. Yeah, it's very easy to see how any two minima, two local minima, will have this. It's just a special case of that geometry. So I'm saying, like, if I connect the 0 and the I of b in that surface, this surface is my functional. In this case, from R2 to R. Then I look, imagine not only the red path, but any connection between B and C. So it can be crazy because I'm just, it only has to be continuous. But it can be crazy, meanwhile it is within the surface because it's composed there. So it can be crazy. It can be anything. And what I'm saying is that I will look at all the maximums of all those paths. And I'm saying I will have a critical point, a mountain pass, in the minimum of it, in the infimum. So in this case, I look like, for example, the red one. Of course, it can be any other that has this. And it's called the mountain pass because even it can be proven that that critical point is not minima nor maxima, but a saddle point indeed. And that's it. So I am saying that if I have some geometric conditions, also this Alice Mail thing, I will have a critical point and I can find it there. So it's connecting paths. And of course, well, I think it's I want you to have this image clear. Like it has some technical definitions that we have to address, but the idea is very simple. The path itself is what? I don't like. Yeah. You mean why infimum?
The red line.
Yeah. Yeah, I can have something different.
Yeah.
I think like in this version, you can have a version where you can find. No, the path is not unique. No, it was the path is not unique. Imagine just a little deviation and then because it's like
It's possible to
of a path. Like there's a version of it which is due to Richard Courant, which is like also very renowned mathematician that has a version done for exclusively finite dimensional, but it's similar like this. That to prove this, we will do it very differently, but he constructs exactly the path. But it needs very topological things. Like, but there's a way. So, but in this, the proof that we are going to see is very non-constructive in that regard. So we cannot see a path, like, or an example. So in general is an it can be infinite paths passing.
So maybe we're noting that C star is not attained in the following sense. It does not claim that there is a path such that C star is the maximum of that path. It claim that from all the paths taking their maxima, could be that every path actually goes strictly above C star and only at some limit somewhere. There isn't any claim that there is a.
Thank you. So yeah, so that's the theorem we have in our heads. How it works. It was investigated by Coran because he wanted an example of a function, kind of natural function that has a critical point that is not maxima nor minima, but a saddle point, because he wanted to understand saddle points. But it was investigated by Ambrosetti and Rabinowitz for hugely different reasons, which are to use that theorem in something called variational calculus, which is a tool to solve partial differential equations. It's non-trivial how one goes from this to that, but it's fun. Maybe I do a 5-minute talk about it. But this article has like 6,000 citations because it's very important or very useful to solve some of high-level partial differential equations, and that's why it became famous. Also, it's interesting in the context of reverse mathematics, as we will see next. So, we can do a lot of analysis on subsystems of SEP2, and I will pass this a little bit quickly, but remember, we have in RCIC the definition of real numbers as quickly converging Cauchy sequences of rational numbers, which mean formally that. We can extend this to complete separable metric spaces. The definition is for a code or for a complete separable metric space is a non-empty set of the naturals together with the sequence of real numbers with the usual properties of a metric, pseudometric in this case. So if we want to assert that something is a metric space, we have to give the non-empty set and the metric. And we say that a point of x, and we say that the point of x is a sequence of elements exactly with the same property of being quickly convergent Cauchy sequences in this sense. And we use the x in x to mean that. We identify the constant, the elements of the non-empty set of the naturals with constant sequences, and this would be precisely, as it's clear, the separable then set, subset of x. Then we just define the distance between points to mean this. And this limit is just the usual for epsilon exists. Important thing, we can also do it for Banach spaces. We just have to have access to the vectorial structure and to have a norm. But as always, we can see a norm space as a metric. And of course, the same with the Hilbert space. We just define the scalar product. It's very easy to, and we have like every Hilbert space can be seen as a Banach one by doing that. This is basic analysis. The thing is that you can do it within RCA0. So now we need a lot of steps to really construct the proof of the momentum bastionen. It is a case in which the forward direction will be heavier than the reversal. So we will go step by step, but first with the most easiest part. This is
Are
Yes.
you allowing zeros?
Sorry?
Are you allowing the norm to take value 0? So you have the norm goes from e to r,
Yes.
right? It cannot be negative.
Yeah.
But you're allowing value 0, so you could have 2 points.
And you have
Two rational points that have.
Yes. But you have to collide them. Well, I think you can only have the norm 0 if and only if the vector is 0 itself, right? So
Yeah,
like,
so why do you clarify that?
but we need to, because the equality in the is defined by that.
Yeah, but that's on E.
It's symmetrical already, maybe.
But an E hat.
Exactly. Yes. Yeah, I think do this.
Yeah, well, so on the pre hat it's pseudometric, but on E it's a proper.
It is. Metric. Yes, thank you. So we have access to this, and the idea is we can work with all the properties we already know about these spaces. So the first thing, and will be very important, is that we want to argue of existence of the code within the systems, the formalized systems of this space. You know, continuous functions from 0, 1 to h such that are fixed. You know, that g of 0 is 0 and g of 1 is b for any fixed b in h, which is the countable subset. Well, I should call it h and h hat. So how we do that is very simple. Take between bars h to be the set of codes of non-empty finite sequences of elements of q cross h, which each of them is a pair, such that the first one is 0, the last one is 1, and the q's are representing the line. Like the idea is, and we order it increasingly. The idea is just I am coding piecewise linear function. So I have to define a line between 2 points, but this is just, you know, the line between 2 points in Euclidean geometry. That's a version of it in any Banach space. And I do that just to define a piecewise function like this. So I am coding continuous piecewise linear functions with breakpoints in the rationals, and this is my set X, which are just codes like this. So they are a subset of N. Now I will define the metric, which is the only thing I need. But this we must use a Wiconix lemma. This is just following a construction that Simpson does, but for R, and he uses the not he doesn't use piecewise linear, but a polynomial approximation of continuous functions that we cannot do here because we don't have access to a product. But it's exactly the same. So in a way, we are already in Wiconix lemma because I want to define the metric as this. So taking two elements of my space between bars h, I define my G's as precisely the piecewise continuous functions, piecewise linear functions with exactly these breakpoints. I want to define that maxima. But that maxima would only have sense in general in Weak-Conics lemma, because just Weak-Conics lemma is the one that will allow us to prove that such a maximum of a continuous function like that exists. Of course, the norm, the difference, the composition will be still continuous, and we have. So this is a very easy way to have access to that. It's not difficult at all. If we don't put the condition of G0, 0, and G1, B, we can indeed prove that the set of continuous functions from 0, 1 is a norm space, a Banach space. Here we only have a metric space because, of course, when we put two functions to be settled in the fixed in the points, it won't be even a vectorial space. Yeah, you're exactly. No, but I think you're right in the sense that if in this case, we have these functions as piecewise linear, right? We already know that they are uniformly continuous. So then even, and also if like the norm is also, if we can prove that I think it can be done RCA0. Like we really don't need the power. I just put it like it's we connect them. But also that is the max. It is important, but you are right. Like, but I think we can, as we have, as you say, like not just continuous but uniform continuous, and we can prove that in RCA0. I think we connect them shouldn't be. And then that's important. Okay, thank you. Yeah, so that'd be the difference. Yes, I think yeah. Exactly. Like we can change the max for sup and we can still in RCA0. Since we will prove all of the things in Weak-Conics lemma, I can put that way. But if we want to be very rigorous, like it's not necessary because we only need a distance. Like we have to treat this as a metric space, so it won't be important.
So I think that max all of gamma.
Like when we do like of course, and finally, we define the completion of this set will be R gamma. Now, the last step will be to prove that if really we construct it like this way, it's indeed in a canonical one-on-one correspondence to continuous functions, each value functions on the interval 0, 1 with fixed images. But that is a kind of easy exercise, as you see in this theorem. Well, it's not trivial at all, but if you have a continuous h-value function defined on 0, 1 such that f0 is equal to 0 and f1 is b, then 1. If it's uniformly continuous, then for each epsilon greater than 0, there exists a piecewise linear continuous function f with rational breakpoints and the fixed end and beginning and end, such that the norm of x minus fx is less than epsilon. And this is the first one is the proof is just an exercise of reanalysis. Very interesting. We need the uniform continuous here. So really we are our gamma is in direct correspondence with not only h-valued functions but h-valued uniform continuous function. And the part 2, which is like the one that makes us see how we always can approximate any continuous function with this piecewise continuous ones. It's just the use of sigma 0 1 induction on the one. So this is guided by Simpson. Simpson does almost the same, but with polynomials. But you can just arrange the things. There is not much. So this is the easy part of the whole of it. Any questions about this? This should be like, it's clear, the construction is clear, the code of the then set, and this is a nice but just analytical proof. This part is the only one that we need to care about the induction. Now the headache, the real headache, because yes. In what sense? Like, well, when I say piecewise linear function here, I mean these codes that I'm calling them, which is just the code of the breakpoints, right? The list of the breakpoints. But you can imagine, because of course it's how to code this, like this pairs. So that I am calling a piecewise linear function. But always talking in a code, like in reverse math. In reverse math we do that, you know. I will call it metric spaces, but they are just codes, and also this. Cool. So now the real headache. So I will also need not only access to that gamma, but I will also need some access to solutions to ordinary differential equations. And this is too much, but let's go. So this theorem is just a generalization of something done by Simpson in RCAC. So we have a separable Banach space in parentheses finite dimension. I will say why. And maybe you have seen this kind of theorem. So we have a function from R cross E to E that has a modulus of uniform continuity. Let's call it that H, and satisfies the elliptic condition with respect to the second variable, as you see, and also has a bound where in this whenever x the absolute value of x minus x0 is less or equal than a, and whenever y, y1, y2 should be there's a typo in this ball. So I'm saying in this interval cross this ball, I have a bound and I have a Lipschitz condition. Given the things that are given are a, b, of course x0 and u. If I have this kind of initial value problem, which is a OGE, a classical OGE, the prima just means derivation with respect to that variable. Then it has a unique solution, and I can have a local solution. in this interval. So this is a proof done by Picard, which uses iterated. It transforms this in an integral equation, and it uses a kind of Banach. I have seen this also in my when I was very young in my undergrad. I don't know if you have seen the idea of the iterations of Picard. That first you transform this into an integral equation, and then you define a functional that keeps iterating, so you can find a solution. It's kind of heavy, but it works, and Simpson proved that it works really in RC0. It's Banach extraction, exactly. But Simpson, but it's needed the uniform continuity that you have there. So of course, in a way, you can say if you, instead of putting RCA0, you put Wiconix lemma, you will have if this ball B of center U and radius B, it's compact, since the interval is, in that cross, you will have immediately the modulus, because it's compact, and Wiconix lemma can prove that in a compact the function has this modulus of uniform continuity. So it works only if it's following Simpson, if this ball is compact. But that only happens if it's of finite dimension. That's the theorem of analysis. If I want to follow the Simpson proof, I will have to make it finite dimension. But we are working in, because it would be cool in finite dimension, because it's, if I want to speak about mountains, I only need R2. But as I told you, like I need, if I really want to grasp the real power of this, I really need the non-finite dimension. So we still are working, or I'm still thinking how to avoid that. There are other forms to prove this theorem in a meta language in the real world, but they need spaces. So that's why we first just saw at Simpson, and because it's already done, and just make the nuances. But yeah, it appears to be just working on finite dimension. Anyway, like if I have an OD, I have a solution in a local solution. But for the theorem, for the use on the theorem, on the Mountain Pass Theorem, I don't need a local solution. I need to know what my interval is. So, but that is very easy, because the only things I do is like I need to my space E open, to be open, which just means that I can code the balls, like somehow, like I can see E as the union of certain balls. Let's put it like this, informally like this, and I have my modulus of continuity, and my new hypothesis is that it's locally Lipschitz, but in an effective way, which just means that I know which Lipschitz constant has in each of these balls that are in that construct the whole space. Then, if I also put the hypothesis that my bound it's less or equal than 1, then I can choose the interval of definition of my solution to be 0, 1. We did in fact more of this. For the Mountain Pass Theorem, we will only need this part, but we also proved that you don't need the bound to be less or equal than 1. You can have any bound, or even some sense of effective local boundedness, and still choose your interval. Not only 0, 1, but any interval. And indeed, with the step of sigma 0, 1 induction, we can even find that kind of IVPs have solutions in all the reals. Like it's a Banach space, but that can be characterized like this. So open in the sense of the code, I have access to the code. Yes. Yes. Exactly. Even what? Yes. Yeah, I put it like to remind you that open in reverse mathematics means this coding of the basic balls, you know. Exactly. And indeed, the proof is like choosing this wisely. So it's a trick, like it's a very cheap trick, but it does the work. Yeah. It should be. It should be buffer because this is proof using Sims, so it should be. For now, maybe I can get the non-finite dimension. It's harder, and yeah, and it's non-trivial at all. And but yeah, and but I didn't put it because I'm not sure of my proof yet. Well, Simpson really does not. His f is from R cross R, so he does this. Exactly. So, and the thing is that he uses the compactness of the. Exactly. So, well, but let's say this. Well, this of course goes. So the point is, I will need to be defined on 0, 1. So I can choose what is my interval. The solution depends not only on the value x, but in the data, right? So I'm saying for each u, then I have a solution. So we can talk about the solution y or phi not only be dependent of x but of u. So I want to I can talk because of the uniqueness of this kind of function. To emphasize y equal y of x and u, to emphasize that it's determined by the initial data and the x. I call it like that, which solves this. This is just a matter of. But, and this is other tricky part, because I want to assess that kind of function is not only continuous in the x, which is in the u. Like, this is a very important thing in ODEs because you have, is what they call the well-posed problem. Like, it's continuous. With respect to the initial values, in this case, the u. The nature of the proof of Picards provides the procedure to obtain the solution that are uniform in u. But not in this sense. I say that is abuse interpretation because I am not claiming that the y is continuous in all the cross space in the cross product, but while fixing these ones, and changing just the elements of E, I can have also continuity with respect to that. But that's tricky also, because even in the meta language, to prove that the U, there is a continuity with respect to initial values, is kind of very, very non-trivial. But yeah, I will say that. So the theorem that we will be using eventually in the Mountain Pass Theorem, which apparently I won't talk today, is this one. I have a solution of these kind of things. So with this continuous in both of them. And this is very important for, well, the next part. So yeah, I will state the most important part of this research. So first, this is just the definition of a sublevel. We have the set I of A is just all the x's in the space, such as the images below A. That's a sublevel. And here is a cool thing called the deformation lemma. I can. So look at this. The following is probable in RCA0. Let the H be a separable Hilbert space, and let I be C11 that satisfies PS, and suppose you have C in R and some positive epsilon bar. If C is not a critical value, then there is some smaller number epsilon, and I'm going to call it that deformation eta, such that does do this. So this is it's a deformation lemma, because what it's saying is that, you have a level. This is we always have I of C plus E as a superset of I C minus E. The deformation means that if you see the variables in 0, 1 as time, at the end of my deformation, this will be shrink into this. That's why it's a deformation. Also, it's continuous. And there is a set, meaning this one, which doesn't move, because at the final stage, at 1, it is the same. So I am just saying there's a difference. In the absence of a critical value, I can find a deformation. I can find a very small epsilon, such that these I have a deformation between these sublevels. This can be done in RCA0, but this is not the thing that we will want to do because of the following. Suppose that I have that, and I want to use this deformation lemma to prove the Mountain Pass Theorem, as in the classical proof, the one that you can find in the analysis textbooks. We should be able to reason to the existence of that C star. And we can indeed prove in Wiconic's lemma that this kind of function that takes a path in gamma and do this maxima of that composition, we can code as a function in RCA0. But if I want to really have access to the infimum, I will need a C0, because that is equivalent. Every sequence of real numbers bounded from below has an infimum, needs the power of a C0. So the analysts, they just prove that something is bounded from below, and they say, yeah, I have access to that. And then I assume that this is what the Mountain Pass Theorem says, that there in C star, I have a critical point, a critical value. Assume not. If not, use the deformation lemma. That deformation then we will appear contradiction, so the theorem is proved in 2 lines. But I don't want to go so far as AC0. I don't want to say that C star exists. What I need is to get away for remaining weakness lemma and not treat C star as an existing real, but look for other tools that allow us to prove the existence of some real with that once found happens to be the futures of an infimum. It is to be the greatest lower bound. And that was the most difficult part of this forward direction, because we needed to do a circumvallation of the method theoretical proof to formalize it and to remain in weak conics. So that it's for tomorrow, because I am which is the most interesting part now. We just gave some very easy facts.